This section is about cylinders and quadratic surfaces. So we've already looked at planes and at spheres. So now we have two other types of surfaces, cylinders, which we've kind of looked at already, and quadratic surfaces. In order to sketch the graph of a surface, we look at the curves of the intersection of the surface with the planes parallel to the coordinate planes. So these curves are called traces or cross sections of the surface. For example, it says sketch the graph of the surface z equals x squared. Now think about a 2D plane because I think that's helpful. If you think about z equals x squared, you have a parabola that looks like this. So we are going to put this into a 3D plane, and this means that notice the y is not there at all. So I'm going to draw this with kind of a pencil tool, and it's not very bright, but what we have here is we have these x values, and y could be anything. It doesn't matter what y is. So it kind of moves parallel to the y-axis. You can see this happening here. So I'm going to go across. I'm not going to put very many more in, but you can see this happening. So we have what we call here a parabolic cylinder. So this is a parabolic cylinder. Hopefully you can read that. The pencil tool is not that great. So this is the front of our parabolic cylinder, and it's kind of a sheet of paper folded in the shape of a parabola. And this would be the back of our parabolic cylinder, so you can see it coming up through. Now, what we do is the cylinder has lines that we call rulings, and they're parallel to a given line. So the rulings in this case would be parallel to y. So we have the shape of the parabola, but the rulings look like this. They are lines that run in this form parallel to the y-axis. So those are the linings or the traces of the parabolic cylinder. And this graph is made up of infinitely many shifted copies of the same parabola. So you can see that it's a parabolic cylinder where it comes from. And I think in this section, it's easier to think about them in terms of 2D and then draw them in 3D. So in my 3D, I probably should outline my curve. It looks like this, just because it has to have a beginning and an end. So this is the back coming up. And then we have the back coming through. Technically, we could have more lines in there, but we basically have one parabola that begins it. Let me show this to you according to what your textbook has. You can see the parabolic cylinder here. Theirs is prettier than mine, but you still get the right idea. So let's look at the next example. It says identify and sketch the surfaces. The first one is x squared plus y squared equals 1. Well, we know this is a circle in 2D, so it becomes a cylinder in 3Z, and the Z value doesn't matter. I like to draw these in pencil because then you can kind of sketch it out. So here we have a cylinder, and it has a radius of 1. So we have a cylinder here, so you can kind of see the cylindrical happening, and the Z value doesn't matter. So technically Z could be anything, Z could be K, and that's what moves these circles. See the circles happening up and down the cylinder. We technically should draw the front. I can't do it that way and draw dotted lines in the back, but my dotted lines in the back don't work out. It works out better for me to erase part of those dotted lines and say, there we have dotted lines in the back. So you can kind of see that's the back of the cylinder. And that was an interesting one there. And then if you need to, we could darken it to say we have a cylinder here, and it looks like this. So, all right, letter B is very similar. It says y squared plus z squared equals 1. So if we had a 2D with just y and z, we still have a circle with 1. So again, we're going to look at it this way, but this time it's going to be centered around x, where x could be anything. I'm just going to draw it in like this. So we have a cylinder where x could be any value. So we're going to say x equals 1. Now the traces would be the lines parallel happening here. Oh, those kind of blend in. Let's try them with a different color. So the traces would be the lines that are parallel to the reason they go this way and not in circles is because your traces continue infinitely in both directions. So they don't end just because we stop to the part of the picture because we know the cylinder continues infinitely in all directions. Therefore, the traces on this one go this way because they continue on all the way around infinitely in both directions. So in the first one, your traces are parallel to the z-axis. And in the second one, the x is missing and the traces are parallel to the x-axis. So when you're dealing with surface, recognize that that these types of equations give you cylinders and not circles. Now, if we were looking only in the xy plane, it would be this circle centered around the origin, and it would have a radius of 1. So we would say that is x squared plus y squared equals 1, and z equals 0. When z equals 0, we just have that one circle sitting right there around the axis. That's your difference between 2D and 3D. The 2D is just a circle, and the 3D is the cylinder. So I think they're kind of fun. Next, we have quadratic surfaces. Now, let's remember a little bit about quadratic surfaces before we get into this. So in our quadratic surfaces, first of all, x squared plus y squared equals r squared is a circle. So we saw that in our cylinder before, but let's just talk 2D right here. So we're going to be in R2. Let's be specifically here in R2. And so x squared plus y squared equals r squared is a circle. And then we have x squared over a squared plus y squared over b squared equals 1. Now, when we look at this in a different form, we say ax squared plus by squared equals capital C. And this is an ellipse. So the difference between the ellipse and the circle is they both have a plus, but the ellipse has different coefficients. See the different coefficients going on there? So that's important to see. The third one is x squared over a squared minus y squared over b squared equals 1, or y squared over a squared minus x squared over b squared equals 1. Now these are both hyperbolas. We'd say ax squared minus by squared equals c, and ax squared, ay squared minus bx squared equals c. So these are hyperbolas. When you see these in 3D, they're going to follow very similar patterns. Notice the minus here. The minus gives you a hyperbola. And as we talked about before, we might as well throw the other conic on here, that y equals x squared, or x equals y squared is a parabola. So if you keep that in mind, then as we move into the quadratic surfaces in 3 space, you have to take it apart and look at them in pieces. So let's look at quadratic surfaces in 3 space. Let's use an example because the examples are nice. In an example, we are given x squared plus y squared over 9 plus z squared over 4 equals 1. So the first thing we want to do is we want to let z equal 0. If we let z equal 0, and remember that means z could be anything. So we're going to say parentheses z equals k, because z equals 0 gives us one flat, and z equals k gives us a 3D version. So let's start with z equals 0. Let's not put z equals k yet. If z equals 0, we have x squared plus y squared over 9 equals 1. Now hopefully you see an ellipse here. So this would be an ellipse with the major axis of the square root of 9, which is 3. So a equals 3 on the y-axis. And on the x-axis, b equals 1. So if you think about the ellipse, it would be 3 and 1. So we'd have an ellipse that looks like this. So that's important to note. And I'm going to go ahead and say that if we put this into 3 space, we're still going to hit that 1 value here on x, and we're going to hit the 3 value on y. So it's kind of going to form an elliptical shape that runs through. It's not kind of. It's going to form an elliptical shape that runs through this way. So I'm going to go 1, 2, 3, 1, 2, 3, and then it's 1 up and back. So it's an ellipse that looks like this. I'm using my pencil mode because I'm going to kind of sketch out that ellipse. So that's the ellipse. And if we put it into 3D, at this point it would form a cylinder. It would form an elliptical shaped cylinder, but it's not the only piece to the problem, because in our problem up here we have a whole lot more than just that ellipse. So let's go back to the next piece. Let's look at it in green, and let's let y equal 0. And at some point y is going to equal k, but we're not going to get there yet. So we have y squared plus, I'm sorry, we let y equal 0. So we have x squared plus z squared over 4 equals 1. This is an ellipse, and its major axis is on the z. So again, a equals 2 and b equals 1 on the x. So if we were to call this z, and let's call this x is going to be 1 still, and z is going to be 2. So here we have an elliptical shape. It's kind of a wiggly elliptical shape. And then let's go ahead and bring this over to our 3D. Now when we come to 3D, we're going to have 2 on the z-axis. So here's 1, 2, and we still have 1 on the x-axis. Let's draw this z-axis down. And here we have 1 here, 2. So it's gonna be an ellipse running through here. So we're looking at the intersection of these, but we're not done. We have 1 more. So this is my ellipse happening when we let y equal 0. Now if y equals k, it would be a cylinder, but again, that's not the only piece of it. So now let's go back and let's let x equal 0. If we let x equal 0 or let x equal k in our future reference, then we're going to say y squared over 9 plus z squared over 4 equals 1. Now in 2D, this is an ellipse, and our major axis is on the y with a equal to 3, and our minor axis is on the z with b equals 2. So let's draw that in here. So we're going to hit the ellipse that goes through these two. And here we have our elliptical shape. I know I should have just gone. There we go. If you kind of swirl it, you can kind of see the ellipse happening here. The blue one's very faint now because the red one's very deep. So what we have is we have an egg shape all the way around. This is called an ellipsoid because all of its traces are ellipses. So this is called an ellipsoid. All of its traces are ellipses. And this is the figure that we have. Let me show it to you from your book so you can get a really good picture of it, but I think mine's kind of pretty. Hopefully yours is as well. So here you can see the pretty ellipsoid happening. A couple things to note real quick is the symmetry. Here it has symmetry with respect to the x-axis, the y-axis, and the z-axis. But if you look, we have an even power of x, y, and z. Therefore, the symmetry is pretty. And all of the traces are ellipses. So we have traces parallel to the xy axis. I decided to try to match the colors I used before. So you could see, we could draw a whole bunch of traces. We could draw the front and dot it in the back. But I'm just going to draw some ellipses here. And then we have parallel to the YZ axis. So we have these traces going this way. And there's a bunch of them. And then we have the traces parallel to the XZ. They are also vertical. I'm not going to draw them in. We're just going to move to the next example. In this example, we're supposed to use traces to sketch z equals 4x squared plus y squared. So last time I started with z, I started with the back. Let's start with x this time. Let's let x equal 0. Remember that eventually x equals k when we hit 3D. So since x equals 0, then we know that z equals y squared. And when x equals k, then we can say that z equals y squared plus 4k squared. So that's what takes our parabola and moves it from 2D into 3D. Remember that this is a parabola, so we're intersecting the xz plane. I'm just gonna, this would be a parabola opening up. So let's talk about the parabola in the xz plane. I'm not gonna draw the negatives here because I'm just gonna try to draw it here. So this is our parabola when we're hitting the xz plane. But remember, there's not just one of them. when x equals 0, we're sitting right there on the axis. When x equals 1, it moves. So we have a bunch of parabolas here running parallel, but it's not the only one we have. So let's just build this as this is the base, this is the beginning one. So now let's look at the next part of this equation, and let's let y equals 0. When y equals 0, then z equals 4x squared, which is a skinny parabola. It's stretched. So when y equals k, then we have that z equals 4x squared plus k squared. And again, we have a bunch of parabolas, but this is a skinny parabola sitting in, we're going to put it at the origin, and it's sitting in the xz plane. So we have a skinny parabola hanging out somewhere in here. Now remember, there's bunches of them, but we're going to have to connect all these values. Not values, but 3D graphs. All right, so now we're going to let z equal 0. And when z equals 0, we have 4x squared plus y squared equals 0, which is nice and pretty, but let's call it 4x squared. When z equals k, then 4x squared plus y squared equals k. Now you can see that that's an ellipse. It's an ellipse where if you were to divide by 4, we would say x squared plus y squared over 4 equals 4. So we have an ellipse, and our major axis is 2, and our minor axis is 1. So that means we're going to draw an ellipse in this craziness, and it has a major axis of 2 and a minor axis of 1, and it hits around in here. So what this does is this is an elliptical shaped parabola. So you can see the ellipses happening as it goes up, kind of connecting the parabola. So these are the traces we have. The blue is the parabola when x equals k, and the green is the parabola when y equals k, and the ellipses are when z equals k. Those are our trace markings. So we could draw bunches of them. But because of all of this, you can see the elliptical paraboloid, so it's called an elliptic paraboloid. An elliptic paraboloid. Now let me bring in the pretty picture because, it's helpful. So you can kind of see the trace markings happening, the two parabolas as well as the ellipse in the middle. All right, let's look at this example. It says z equals y squared minus x squared. So let's start off with, let's let x equal 0. So that means z equals y squared. So when x equals k, we get z equals y squared minus k squared. Now, you can see that this is a parabola, so z equals y squared is a parabola opening up. And the minus k squared means it moves down. So in 2D, what we would have is we would have a parabola that sits on the axis, or that minus k moves it down. So you have that kind of a look. And this is going to be an interesting 3D graph. So let's start with the 3D graph. And this piece is going to be parabolas, and these parabolas are moving around. So this first parabola sits right here on the axis. I'm going to use lots of colors here. And then the second parabola would be, if it moves down 1, it would move, if you think about it moving down 1, that means it intersects the axis at -1 and +1. So if this is y and this is z, so it would hit over here at -1 and over here at +1. So we have a parabola that looks like this. And then if it moves down, like say 4, then it hits over here at -2 and +2. So we could have another one that looks like this. So we have a family of parabolas moving around. All right, now let's talk about if we let y equal 0, then z equals -x squared, which is an upside down parabola. And it's going to follow similar patterns, but we're going to look at it carefully. So this means y equals k, so z equals -x squared plus k. So if you think about that upside down parabola moving up and down, I'm going to draw it in a separate over here. So in the first place, we have an upside down parabola, and it looks very similar to the last one, but we're kind of hitting the xz plane and not the yz. So as we look at this, this will be x and this will be z. This parabola starts out at the axis, and then it moves up. When it moves up, think about the fact that it crosses at positive -1. Positive -1 for x. So that means it would be hitting back here and here. So I probably didn't draw my first one well. It's okay. That feels like it's a better parabola. And then the third one, if we crossed at, let's move it up 4, that means we cross at positive -2. So here's positive 2 and here's -2 out here. So we have this parabola happening out here. So we have these parabolas that are traveling along the axis. So we could have, let's erase this blue one and draw it so it kind of meets the rest. So it's parallel to the rest. It makes a little more sense that way. So you can kind of see it sitting now on the XZ axis. So we've got some crazy things going on. And now let's let Z equal 0. So if we let Z equal 0, then we have 0 equals y squared minus x squared. If we let Z equal k, moving it into the 3D, then we know that k equals y squared minus x squared, which is a hyperbola. Now on this hyperbola, oh, this is so not exciting to draw in 3D. I'm just telling you now. If you think about a hyperbola, let's do, you draw your box because they're both 1, and you draw your traces, and y is positive, so it's going to open up and down. So what we've got is we've got it happening in lots of spaces. So let's draw our axis lines. Oh, it's going through x and y. So it'll go through here and through here. That means that it sits on your y-axis here. And if we let then it can move up and down. It can move according to, now if we let k be -1, we also have this trace here. So it comes up to be both. It would be this one because your major axis becomes x. I missed my lines right there. By the way, these traces off to the side, these are the traces that are happening when we build this figure. So what we have is we have a parabola for this first piece, we have a parabola. For this piece, we have a parabola. And for this piece, we have the hyperbola. So if you can kind of think about the way this is going, this is interesting because as we put the 3 of them together into our 3D space, the top piece, when we let x equals 0 in the YZ plane, we have a parabola that's opening up. So these sketches are easier to do with a pencil. And then we let y equals 0, and we have a parabola of the same width opening down on the XZ plane. So it's tilted a little. I guess let's tilt that a little. So it feels like it's tilted a little. It's not directly underneath the other. And then we have, when we let z equal 0, we have a hyperbola. Now that hyperbola comes out, and it comes out from the xy plane. Mine's not close enough, but my red parabola is not wide enough. So it ends up being kind of a saddle because you have these parabolas, these blue parabolas that run this way. So they run down and you have a 3D looking shape here. And then we have these red parabolas. Like I said, I didn't draw mine heavy enough or wide enough. So I'm going to draw it wider now. And you can kind of say it flips in there. So you have these. And then you have the green. And it kind of connects to all of this. So when you get done, it looks like a saddle. Mine does not. I understand that yours may not. I'm looking for you to know that it's a hyperbolic. It's called a hyperbolic paraboloid. And the reason it's called that is because we have a hyperbola mixed in with our parabolas. So this is called a hyperbolic paraboloid. And let me show you what it looks like in the book because it's prettier than mine. So here you can see two different views. I kind of, if you were to make my pencil and connect it all together, I kind of have close to one of them, maybe. All right, so let's look at the next one. Just know that it's a hyperbolic paraboloid and come up with what you need to make that happen. So the next example says to sketch the surface x squared over 4 plus y squared minus z squared over 4 equals 1. Notice these are all quadratics. That's why they're called quadratic surfaces. So let's start with x equals 0. I like to start with y with z, but let's start with x equals 0. And then we have y squared minus z squared over 4 equals 1. So this is a hyperbola. And like we learned before, this is a lot of hyperbolas. So when we do x equals 0, we have the major axis is a equals 2, and the minor axis is b equals 1. So we have this shape, and z is up here. So z is 2, and it goes up and down. So in our 3D space, that means we're hitting this at 2 and negative 2. And the y values go to 1 and negative 1. So this is my box, and this gives me my lines to draw so that I can draw my y is positive, so it's going to go this way on the y. So this is our hyperbola facing this way. Now remember, this was 2D, and and we're going 3D. So as we swing it 3D, it's a lot. It's continuing out this way. It's continuing out. So we're combining more than one, but this gives us the base for it. We're combining more than one of these values, figures, surfaces. All right, so now let's switch to, let's let y equal 0. When we let y equal 0, we have x squared over 4 minus z squared over 4 equals 1. So here we have a hyperbola where both values are 2, x and z, and it's opening on the x-axis. So that's going to help us draw it over here. Let's move to our 3D space. Z is 2 and x is 2. So that would give us this box, these 4 points, because it's up 2 and down 2. It's not really a box, but it's close. So then we would draw our lines through here to form our parabola. And it's going to be really close looking to the x-axis. And then our box, our parabola goes through this value. And it sits on the box. Our hyperbola goes through this value and sits on the box. So what we have is we have two hyperbolas happening here. And now we let z equal 0. So if z equals 0, then we have x squared over 4 plus y squared equals 1. Now that's an ellipse, so that's going to be pretty nice, where our major axis is x and our minor axis is y of 1. So normally x is 2 and y is 1, so we have an ellipse that looks like this. So we're going to connect this 3D graph with ellipses that have a major axis of 2, and then the y is 1, and when the y is the same value of 1, it's an ellipse that draws it together. So we have an ellipse here. The traces are ellipses. So these ellipses, these ellipses. So it kind of brings it all together to be an elliptical. This is called a hyperbola of one sheet. I didn't do a very good job of drawing that in 3D. So I'm going to kill it and I'm going to erase it. I'm not going to erase it. I'm going to come down here and use these values that we know and try to draw it a little bit better at this point. So that would be how we build it, but let's see if I can build it a little bit better for you. So what we're going to do is we have hyperbolas, and the y value is 1, and the x value is 2, and those are going to make an ellipse. and the z value is 2. But the ellipses continue the z values up. So what we have is we have an ellipse that goes through here, and it makes hyperbolas going out. So we're going to say hyperbola is going out, and we're going to draw it out through here. So this is the ellipses moving up, and we know that the z forms these ellipses as well. So you can see a little bit better. This is called a hyperboloid of one sheet. If we were to look at the x and z ones are hyperbolas happening in there as well. It's not drawn as beautifully as it could be. I can bring in the one from the book, but it is important to note that this is a hyperboloid of one sheet. The reason it's a hyperboloid of one sheet is I want you to catch right here. We have one hyperbola here. It forms two hyperbolas, but it's one sheet. It's a hyperbola being formed by one. So we have two hyperbolas being connected by ellipses. So the traces are ellipses and hyperbolas. Let me bring in the picture from the book. So here you can see in their picture all the trace lines and the intercepts. The intercepts are important because this intercept right here, this is what's happening at the axis line for that. And you can see the trace lines coming down through, and they're hitting all of those trace lines as opposed to mine. I can't draw that in such a way as to make it beautiful. Don't worry, what I can't draw, I don't expect you to draw. Just do your best and describe it. Describe it using hyperbolas and things. So the next one says 4x squared minus y squared plus 2z squared plus 4 equals 0. So before you start, notice all the other ones have been equal to 1. So that's what we need to do. We need to take the 4 to the other side. 4x squared minus y squared plus 2z squared equals negative 4. And then you have to divide by negative 4 because it has to be equal to positive 1. So we're going to divide everything by negative 4. By the way, this is going to give us a new shape because notice we have minus x squared plus y squared over 4 minus z squared over 2 equals 1. Then if we let x equals 0, we have y squared. By the way, notice 2 minuses here, so that's going to be a different shape. So y squared over 4 minus z squared over 2 equals 1. So our major axis is 2, our minor axis is the square root of 2, and it's x and z. So if this is y and z, we have 2, and square root of 2 is about 1.4. So we have a hyperbola that looks like this. Now, if we let y equal 0, it gives us a negative, 2 negatives and a positive 1. So we're going to deal with that in a minute. Let's let z equal 0, in which case we have negative x squared plus y squared over 4 equals 1. So again, we have a hyperbola. And your major axis is again y. We're going to put y up here and x here, though. So my major axis is y of 2, and the minor axis is x of 1. So, oops. So we have a hyperbola that opens at y, so up and down. So here you have your hyperbola. So I'm sketching this. It's also opening at y, and it sits on the box. Just it sits on the box a little bit differently. It's more to tilt. So we have this kind of a shape here. So now let's talk about what happens when we let y equals 0. Now before we had an ellipse, so it kind of pulled it all together. So when we let y equal 0, then we have negative x squared minus z squared over 2 equals negative 1. Equals 1. So the problem is we want to call it x squared plus z squared over 2 equals negative 1, but that's a problem. In this first problem, you don't have a form for a quadratic because you have a negative on both. In the second one, you don't have a form for a quadratic because you have a negative 1. It's the same problem written two different ways. So what we need to do is we need to let y equal k. Then we have negative x squared plus k squared over 4 minus z squared over 2 equals 1. So let's move everything around and switch sides. There's lots of ways to get to this next thing. I'm going to say k squared over 4 minus 1 equals positive x squared plus z squared over 2. Now, we're used to seeing it the other way. X squared plus z squared over 2 equals k squared over 4 minus 1. So what we have here is an ellipse. Again, we have this square root of 2 for our major axis and a equals 1 for our minor axis. Now notice this only happens when k is greater than 2. So when k is greater than 2, we can say the absolute value of k is greater than 2. If k is 0, then we have a negative value, so we don't have an ellipse. So what we need is we need to think about this only when k is greater than 2. So then we have ellipses up here. This is an ellipse. And these ellipses are happening when k is greater than 2. So we got an ellipse here, and an ellipse here, and the absolute value of k is greater than 2. So we have these ellipses. So you can see that these two negatives in the beginning caused us an interesting hyperbola, and this is called a hyperboloid of two sheets. A hyperboloid of two sheets. Then we have an interesting example where it says classify the quadratic surface, so it doesn't say sketch. So we have x squared plus 2z squared minus 6x minus y plus 10 equals 0. Well, you can see that we have another x right here, so let's put our x's together. X squared minus 6x plus 2z squared minus y equals negative 10. I'm going to move the 10 to the other side. I might change my mind. So let's complete the square. X squared plus 6x plus 9 plus 2z squared minus y equals negative 10 plus 9. So we're going to have a negative 1 there. That's weird. X minus 3 squared plus 2z squared minus y equals negative 1. Now, if we do like we saw earlier, and let's set that y to the other side. So y equals x minus 3 squared plus 2z squared plus 1. Then we have what we can see as a better look. Then if we let x equal 0, then we have y equals 2z squared plus 9 plus 1 is 10. So that's a parabola. Let's abbreviate it as a parabola. Let's write it out, parabola. I got a little bit of space. If we let z equal 0, then y equals x minus 3 squared plus 1, which is a parabola, but it's centered at 3, 1. It's anchored, or the vertex. The vertex is at 3, 1. And then if we let y equal 0, then we get x minus 3 squared plus 2z squared equals negative 1, which is a problem. So let's put the y back in, and let's let y equal k. Then we have x minus 3 squared plus 2z squared equals k squared minus 1. So k can be anything larger than 1, and this is an ellipse in this case. So we have two parabolas, an ellipse. And if we think about the fact that we have the point, then let's go back up here and make this a 3 space. We have the point 3, 1, and then z was 0. So what we have is we're looking at a paraboloid. Well, we're looking at the fact that we have two parabolas and an ellipse. So if we come right here-ish, let's call it right here at the point 3, 1, 0. Now coming out of that, we have two parabolas and an ellipse. So we have a parabola for y equals z squared. And then we have a parabola for y equals x squared, and it's centered right there. I'm going to draw it inside of here just because it sits on a different curve. And then we have ellipses when y is equal to some value. So now we have a paraboloid. and it sits at the point 310 and opens to the right. So the traces are the parabolas and the ellipse. So here we have examples or applications of quadratic surfaces. Examples of quadratic surfaces can be found in the world around us. The world is considered to be a sphere. We all talk about it as a sphere, but they say a more accurate model is an ellipsoid because the Earth's rotation has caused a flattening at the poles. So that would be an interesting thing to research and look up. Circular paraboloids obtained by rotating a parabola about the axis are used to collect and reflect light, sound, radio, and television signals, like in figure A of a satellite dish. So it'll reflect signals. Letter B shows you nuclear reactors that have cooling towers in the shape of hyperboloids. And letter C, sorry, is gears in the shape of hyperboloids that mesh and rotate along skew axis. So there are lots of examples in the world around us. I'd like to add one more thing. There's a helpful chart that you should look up. This is a very helpful sheet. It's a graph of quadratic surfaces. So if you know your conics, it makes sense, but it kind of helps you pull everything together into one place and think about what you're working with. So this is a helpful graphic to download, and I will post this in Canvas for you. So I hope you learned something and enjoyed this video.